In summary of what I've understood from multiplications of tenses is that everything operates in the basis vector form. Alright, so what do I mean by that? If you were to take dot product u dot v, alright, we will have ui this form, alright, and we know that for the inner product, for the dot product, we are talking about ei dot ej is equals to the Kronecker delta. Correct? This is what we have understood. And the next thing for this thing is that we group all the components or somewhat the constant together, ui vj, and then we dot product the basis, and then we have ui vj Kronecker ij. Alright, this is simply using this understanding. Alright, so now you can see that the inner product or dot product is this. But what is exactly the inner meaning? Alright, u dot v is simply u transpose v. Okay, while the outer product, alright, or the outer product is actually u dyadic v, or the tensor product v, is equals to u vt. Alright, so for the dot product, normally what you would M out is a constant number, alright, a scalar. Alright, for a dyadic product, what you end up is some sort of a matrices. Alright, some matrices. Correct? And as for the cross product, we are gonna talk about having another vector k. Alright, it's some vector. Alright, so as you can see the whole graphical view right now, when you dot product, it's u transpose v, you get this one, some constant c. When you dyadic tensor product, you get uv transpose, you get a matrix. When you cross product, you are just taking back another vector. Okay, while the operations are always the same. Alright, the operations are always the same. Alright, so I just want to give you the key concept over here. Alright, for the inner, you need to memorize this one as the Kronecker delta. For the outer or the dyadic one, alright, ei delta ej, alright, is simply by itself. Alright, it's just like that. Okay, you just leave it like this. Alright, the outer is simply leaving that as that. As for cross product, alright, you have ei cross product with ej. What you have M out is the name of a family, and then with a baby vector k. Alright, this is what I'm saying. This is it. So if you were to take a look in the outer or the dyadic one, alright, if I have, for example, maybe u dyadic v, alright, what I will write down is ui vi, this one, right? It's just the same thing over here, alright, except the sign, this is dot, this is dyadic. Alright, same thing, I group all the components together as one set. And then I'll just simply group the basis vector in one component. And I'll just leave it the case. Alright. Similarly, if I were to do cross product, alright, now maybe I should take this, paste over here. It's the same thing, right? But instead of dyadic, I just change the sign. Alright, I change as a cross. This is a cross product. So similarly, I also group the components. Alright, so I have ui vj, and then this is ei hat cross product with ej hat. Alright, and this cross product, based on this understanding, we can just simply rewrite as ui vj ijk ek. That's all. Alright, now I'm gonna talk to you something different. Alright, just a quick summary is that the dot product is the trace of the outer product or the dyadic product. Alright, so what does this mean? Alright, so if for example I'll take U dyadic V, alright, you know that U dyadic V is simply U V transpose. Okay, I'll just simply write as 1, 2, let's sub in some numbers, alright, 3, 4. If that's the case, what I would have is a 2 by 2 matrix, correct? So it's 3, 1 times 3 is 3, 1 times 4 is 4, 2 times 3 is 6, 2 times 4 is 8. Alright, so the trace is simply the diagonal stuff of here. Alright, if I were to sum them up together, alright, 3 plus 8 is equals to 11. Okay, so this is the answer for dot product. So to prove it, U dot V is equals to UT V, alright, which in this manner is 1, 2, 3, 4. So I have 1 times 3, 3, plus 2 times 4, 8. Therefore I have 11. As you can see, this is simply the dot product with as a trace for the dyadic product. Hope this is pretty clear, and I hope that this concept of inner, outer and cross product is straightforward for you, and the component and the basis vector, everything is operating in terms of the basis vector E. Alright, as you can see, all is E's. So I hope this is a pretty good summary for all the multiplications of tensors. And therefore, in the next video, we'll talk about operators on the tensors. See you there.